Hi everyone, welcome to our next seminar. So these are today's outlines. These are the things that we are going to do today. So the first one is assignment 3, and the second is about a term paper, and the third is about the dummy variable trap, and the fourth is about the F-test, and the fifth one is to um, continue what we just said last time, like the part that talking about the threats to internal validity. So basically, since the deadline of assignment 3 is like on like Thursday at 6 p.m. So actually I don't have enough time to grade them and to finish like all the grading. So I will only put the answers and I will only put the solutions on Athena. And then like next time I will talk about like what I saw generally in assignment. Yes. So this is just like a reminder for your term paper. So remember that the deadline for the preliminary version is on May 13th, and the deadline for the final version is on June 7th. And especially in the final version, you need to upload a PDF file, so which is your like essay and a script file, and also the data set that you used. So basically in the preliminary version, what we focus on is your like paper itself. So you don't need to upload the data set and also your script in your preliminary version. And the preliminary version is presented on the last seminar where you get the feedback. But since now we just have the virus, so um, we will discuss with the lecturer about how to deal with the problem of presentation. So if there is any updates, I will talk to you afterwards, either on Athena or in the video. So now we are going to talk about the perfect multicollinearity and also the dummy variable trap. So one of the assumption for the least square of multiple regression to work is that no regressor can be a perfect linear combination of any other regressor. So what does it mean? So for example, if you would like to know whether there is any like gender gap of wages, so you regress wage on like female. However, if you put like female and male both in a regression and with wage, then actually it is not possible to estimate the effect of a variable because now since you put both female and male in a regression, which means that for data there is no comparison group because now you hold both female and male constant. So actually, you just directly nullify the whole regression. So this is what a perfect multicollinearity means. And the dummy variable trap is a special case of perfect multicollinearity. So which is actually just the example I raised. So for any binary variable, there is a relationship with the inverse of variable. So this is also the assignment that you did, like the assignment 3. So, especially the last question. So if you change like male to female, then what will happen to your regression? So you can see the example in the slide is also actually like example that I just said. So if you put both female and male in your regression, then it is not possible to estimate the gender wage gap because we cannot change one of the binary variables without also changing the another. Because if you control both, actually you just directly stop the whole variable. So in the next assignment, there are multiple binary variables where Stata automatically excluded one of them. So in the multi-binary variable case is that those variable, their sum will be equal to 1. So for example, you can see that like triple 0 equals 1 minus triple 1 minus triple 2 minus triple 3. So like the sum of these four variables equals to 1. And if you put like all of them in the regression, it will cause the dummy variable trap. So there are two ways to solve the problem. Actually, first one is that for Stata, Stata will automatically omit one of them to avoid the crash of the system. But the fact is that actually Stata will only like randomly choose one variable to omit. So you don't know which one like it will omit actually. So for example, in the slides, you can see that Stata omitted the triple 3 here. So which means that for Stata now, triple 3 is the comparison group here. So the coefficient that you see, for example, triple 1 here, like 137 is the difference between triple 1 and triple 3. And the 36 is the difference between triple 2 and triple 3. So in the same like logic, so the minus negative 562 is the difference between triple 0 and triple 3. So Stata will like randomly omitted one variable. So which means that the comparison group is also chosen by Stata. However, if you would like to, for example, use triple 1 as the comparison group, and to see that what's the difference between triple 2 and triple 1 and triple 3 to triple 1 and triple 0 to triple 1, then you should omit triple 1 because the variable which you omit is actually the comparison group, which is also the value in the intercept. So you can see here the 3017.355 is the value of triple 3. So this is the first way to solve the dummy variable trap. And the second is that you could add non-constant option. So if you add the non-constant option, so the data will plus all the will add the value of comparison group back. So you can see that now like all four like variables shows their like original values. So the value of triple 3 is like 3,317, and for example, like triple 1 is 3,454. So you can see that the difference between triple 1 and triple 3 is actually the same as the difference like 137 here. So when you add the non-constant option, actually Stata just added the value of intercept back. So by this way, then you can know the value of like all dummy variables. So yeah, so I explained like why are the estimates for dummy variable different between the two strategies. Because when you add the non-constant option, the stata add the value of intercept back. Because the first one is that stata show the difference between the dummy variables. And the second is they show the like total value of like different time variables. And the second is what does the star after triple mean? So you can see here. So you can see here that the star after the triple. So it's actually one of like the like convenient operations in Stata. So for example, you have some variables which is like triple one, triple two, triple three, and triple zero. So they all have like triple, but they are just different in numbers. So you can just put a star. Then Stata will find all the variables in the data set which contains triple, but just have a variation of numbers. Then you don't need to write like triple zero to triple three. It will like save your time. So this is the meaning of the star after triple. Yeah, so yeah, I answered the yeah, I just actually said what the next slide tried to answer. And now is the F-test. So basically, you can think as F-test as the multi-variable regression version of t-test. So for t-test, you are trying to see whether beta one, like you are trying to test whether the beta is different from a null hypothesis. So a null hypothesis is that like beta equals 0, and the alternative hypothesis is that like the alternative hypothesis is that like beta does not equal to 0. And in the multiple regression, so we test that. So the null hypothesis is that like both or like even more. So it's like beta 1 equals 0 and beta 2 equals 0. So which means that in the alternative hypothesis, so if one of them does not equal to 0, then we actually can reject the null hypothesis, because the opposite of and is or. So you can see in the slides that so the null hypothesis is both of them should be 0. So which means that the alternative hypothesis that if one of them does not equal to 0, then we can reject the null hypothesis. So below is the way that we calculate the F-test in the situation of like two variables. But basically, you can think that F-test is the multiple regression version of t-test. So if you would like to compute the F statistic manually, so you can use the standard error SSR from a restrict model. So the restrict model, which means that you forced some of the variable to be to be 0, so to fit the null hypothesis, and an unrestricted model, so that you just put all the variables directly in the regression. So then you get this formula. But the caveat with this formula is that the caveat with this formula is that to obtain to get this formula, the error should be like homoscedasticity. So I will explain what homoscedasticity means. But basically, for me, you don't really need to remember this formula because this is not really um, useful, honestly speaking, in the like actual operation. Yes. So after you regress this data, so just like what we did when we summarize, so you put the return list, right? So after regression, all the statistics that um, that you get from a regression will temporarily stored in E class. So for the summary, for the statistics, which we get from the summary command, data will store them in the R class, but they classify the result of regression in the E class. So if you would like to access these statistics, then you should type E return list, not only return list. So this is also some other operations if you would like to do the F test in Stata. So you can use the command test to do the F test. So the first test is to test whether all estimates are equal to 0. So you can see here. So the first F test is you directly put triple 0, triple 1, and triple 2, and to see whether like all estimates are equal to 0. So this is what the null hypothesis is. But the second is when you put the equal sign between them, then the second test is to test whether the estimate is the same for all the three variables. So you can see that like in both of tests, the null hypothesis is like clearly rejected because the probability, like the value, like the F statistics is like really big. So one is 11 and the other is 16. So now we will continue like our last introduction to the threats to internal validity of multiple regression. So we just finished the part of omitted variable in our last seminar, and now we're going to continue it. So first one is functional form. So this is somehow important, though like not as important as omitted variables. So I would say that the measure or the major problem in your term paper that you will face is try to like mitigate or reduce the influence of omitted variables. So now we are going to talk about a functional form. So if the true functional form is non-linear, but if we estimate with a linear regression, then we will have a bias. So which means that, for example, the marginal effect of a change in variable may depend on its value as well. So for example, if you want to know the relationship between wage and experience, and you might think that actually experience has diminishing marginal returns. So as you work more and more, like by each year, maybe you don't gain as much from one additional year of experience when you work more and more. So which means that the effect of experience on wage might decrease with an with an increase in experience. So if you don't put the square term of experience in your regression, then actually the estimate that you get from the regression of experience and wage is biased. So this is how the functional form matters in your regression. So to see whether there is any need of putting the quadratic form or cubic form or even like higher degree, actually you can see the scatter plot, for example, between wage and experience to see whether there is any need to put square term or even the higher degree. So the slides gave some example. So you can see that in this example, when we put the square term of experience in the regression, you can see that the square term is negative. So it is negative 0.028. So which means that actually the hypothesis that experience have a marginal return, have a decreasing marginal return, it's somehow like true. So actually it's quite possible that it is like negative because you can see here that the p-value is 0 as well. So the other example is that, so when we try to plot the predicted wage against experience for males working in the public sector, and since we just get that the experience square is negative, so when you plot the predict value against experience, you can see that there will be a peak. And then like after like some certain age, then the wage of like males working in public sectors will start to decrease. So this is what the marginal like decreasing marginal return means here. Another like possible functional form that you can operate is logarithm. So basically, logarithm transform changes in variables from units into percentage. So if you would like to compare the wage gap between public and private or compare wage gaps over time. So comparison in like the absolute number is somehow distracting and not that easy to interpret. Instead, actually, you can use percentage. So for example, if you put log wage here and then like education in the like right hand side of the equation, then you can think that, which means that like what percentage of wage will change if like if one individual increase like one more year of like schooling. So if you find that the relationship that you would like to take the research on is probably nonlinear, so perhaps it will be linear after you take the logarithm, so it can happen. And the other is that the logarithm is also related to elasticity, because folks, because the elasticity is that like how much percentage that y will change if like there is any like percentage change of x. So since logarithm transform changes in variables from units into percentage, then actually you can use the logarithm to calculate the elasticity. So these are three cases of logarithm that you can use in regression. So the first one is that you put logarithm in the right-hand side of the equation. So which means that the coefficient of beta 1 here is that one percentage change in x is associated with a percentage in y of 0.01 beta 1. And like conversely, if you put logarithm in the left-hand side of your equation, so which means that a change in x by 1 unit will associate with 100 beta 1% change in y. So for example, in this case, just like for example, if you think y as like y as wage, and then beta 1 as and then x as education, and you get, for example, 0.1 here. So which means that if you increase like 1 year education, 1 year of schooling more, then the wage will increase by 10%. So this is what the second means. And then the third one is actually the elasticity that we just talked about. So if you put logarithm in the both sides of the equation, then which means that 1% change in x is associated with 1 beta 1% change in y. So beta 1 is the elasticity of y with respect to x. Yeah, so here just comes the most classic example. So the operation of log that we use like the most often in economics is to put the log term in wage. Because actually it's just directly related to what we did, I think in assignment 2. So the reason that why we put log in wage is that the distribution of wage is typically skewed, so it's not normal distribution. So instead of hoping the central limit theorem will smooth the distribution by large sample sizes, actually we can just directly put log to make the distribution of wage look more normal. Because actually we found out that the distribution of log wage look much more normal than the usual distribution of wage. So by this, we can make the distribution of residuals close to normal and make the whole regression like fit its assumption more. So this is why we usually put log in wage in economic research. So let's back to our example. So for example here, you get the value is at 0.03. So which means that as long as you increase one more like year of schooling, then your wage will increase by 3%. Yeah, so this is just what I said. And the third one about the functional form is about categorical form. So the difference between the categorical variables and dummy variable is that the dummy variable only takes value between 0 and 1. But the categorical value is that, I took it in a bit wrong way. So categorical variable can also be regarded as one type of dummy variables. So categorical value is try to group a continuous variable into some different like groups to see the difference between them. So actually it is also a kind of dummy variables. So for example, instead of estimates the return to education by like one additional year of schooling. So what if we would like to know the difference between having a primary, high school, or university education? So which means that we need to create like three different categories: primary, high school, and university from one like more continuous variable, for example, like years of schooling. Although we know that basically, actually like years of schooling is still a bit like discrete because it only takes on like integer. So it's either like 6 or 12 or 16, um, but it's like a series of numbers. But the categorical is that they just group a series of number into one group. And if you don't, if one individual does not belong to this group, and then it will take the value like 0. So it's actually a bit like dummy variables. So how we create multiple binary variables, so which is also categorical variables in Stata. So actually it is the same as what we did when you want to create a dummy variable, but it's just now takes more procedure. So for example, now you would like to generate a category called primary education, so which is from years of schooling 0 to 9. Then you generate primary equal to 0, and then replace primary equals to 1 if like schooling is smaller than 10. And if you would like to generate a time variable called high school, then you generate high school equals to 0, and then replace the value of high school to 1 if schooling is bigger than 9 and smaller than 13. And for university, it's in the same spirit. So this is how we do the categorical variables. And since categorical variable is like one kind of dummy variables, so when you put the categorical variables in your so when you do the categorical variables, you need to keep in mind the dummy variable trap, and at least leave one category out as a like comparison group, or you can say that it's like a reference. So for example, in this regression, the wage is regressed on high school and university. So which implies that now the value of intercept is the value of primary school. So which means that in this regression, the comparison group is the primary school. So the difference here, like 2.63 of high school is the difference between high school and primary school. And the 20 that you see here is the difference between university and primary school. And here comes another kind of function, a kind of functional form is called interaction terms. So the square term is that the value of one variable may depend on itself. And the interaction term is that the effect of one variable might depend on other variables. So for example, you might think that males and females might have different returns to schooling. So which means that the effect of school may depend on gender. So maybe men will benefit more from an additional year of schooling or vice versa. So it can happen. So if you think this might happen, then actually you can put the interaction term between female and school to see like whether like this interaction term has some difference. So which means that the effect of school may be different between male and females. So if you did that, so you can see here, the value is like minus. So which means that the difference in returns to education for females compared to male is on average like lower by 0.15%. However, it's not significant because you can see that the p-value is extremely like large, 0.6. So this is how we operate the interaction term in regression. If you think that the effect of one variable might depend on another variable. So if you didn't consider them, then you might get some problem. So these are some codes that you can use when you do the regression, also the term paper. So you can take a look. So the interaction term means that the effect of schooling is, like in this case, like the effect of schooling depends on gender. So which means that they might have like different slopes. So on the same years of schooling, because in this case it's quite small, so it's not that easy to see, but you can still see that the effect of schooling on men is still a bit stronger than male. So you can see that, for example, if you take 20, then you can see that the value of men is a bit higher than the wage of women. If you if you take a look at it like carefully. So this is the meaning of interaction terms. And the interaction terms is not only in the interaction term between continuous variable and dummy variable. Actually, you can also put the interaction term between dummy variables as well. So for example, if you think that the effect of like studying high school or studying the university might depend on gender, then you can put them in a regression as well. So the interaction term between dummy variables are also fine. So these are also the result of regression. If you put the interaction term between female and university, and also the interaction term of female and high school. So you can see that the return to high school for women is lower than men by roughly 1% less than men, though it's not significant, and like 3.8% lower for women, like in university, though it's not significant as well. So these are the functional form that I try to discuss with you today, that you might be able to use, like that you maybe will use it in your term paper. But actually, the most important question is that, so the purpose of this functional form is to help you like know more about the nature of the topic and the nature of the variable that you would like to use in your data set. So it does not mean that you should use as many different functional forms as possible to show like how good you are in operating those like variables. So this is not the point this is not the reason why I introduced those functional forms. So before you use those functional forms, so you should really think about which one that you should use. So for example, based on your knowledge, you think that like experience like might have decreasing marginal return, or the effect of school might depend on gender. So these are some reasoning. So before you use those different functional forms, you should have reasoning and also a theory behind. So you should, so you shouldn't just use what, you shouldn't you just use the functional form as you want, and just think that as long as I put like as many different forms of like a functional form, then it looks better. So it's not the case. So you should um, ask yourself why you use those functional forms every time before you use them. So this is like today's seminar. And next time we will still continue to introduce like more like things that you should know, like you should keep in mind when you write your term paper. And I will talk about assignment three next time, or I will just like directly put them at on Athena. Yes. So see you next time.